I'd like to talk a little bit more in depth about the field adjustments on the D-Lev, and particularly about the linearization process that it uses. This linearization process is remarkable in that, for two reasons. It linearizes very well. I think the D-Lev, you'll find the D-Lev is more linear than any theremin you've ever encountered in your life. And I don't say that to boast, but it's true, I think. And its linearity is very stable. It doesn't require any adjustment generally, other than what you're used to adjusting, the null point. And once your null point is set, the linearity will fall in place, and you'll be able to play, right up to the antenna without feeling the field cramp up or get weird or do anything. Just anywhere you play it in the field, it'll feel the same. Be able to use the same hand gestures and get the same changes in frequency. So I thought we'd look at, I thought I would explain the procedure and kind of what goes on with the knobs and stuff with the field adjustments. And it's now part of the manual, so if you go to the recent manual anyway, if you go to page 55, you can read this instead of me yakking at you. So what happens in any theremin is we have this graph here. As your hand gets closer to the antenna, the pitch, or the frequency of the antenna, drops somewhat. And as you get really close, it drops an awful lot. And this is just the capacitance of your hand influencing this LC oscillator. So in an analog theremin, what you do is you beat this frequency nonlinearly against a fixed frequency oscillator that's very close to the same frequency. And then you take the byproducts of that mixing, and you use the subtracted byproducts, and you filter out the added byproducts. Like this will generate a very low frequency and a very high frequency if they're both sinusoids. And if you filter out the added frequencies, and you just look at the subtracted frequencies on an analog theremin, you end up with this sort of curve. And this sort of curve here in the mid-range is roughly exponential. And that's really advantageous because then that's your pitch, and you want an exponentially changing pitch. It'll seem linear to your ear because your ear is logarithmic with pitch and with volume, actually, which is weird. So, but as you get closer to the antenna, it gets squirrely. It goes beyond exponential. And as you get near 0 hertz, you can't have a 0 hertz in an exponential system. You can't have 0. It doesn't exist. Things just get smaller and smaller. They can't go to 0. So it obviously gets squirrely here too. So, and it just has to, mathematically even. So in the D-Lev, what do? Well, we have the same situation here, but instead of beating this against a fixed oscillator, we just measure this frequency, and we don't really have to do anything to measure it because the digital phase lock loop is just kicking out numbers anyway, and we can just take those numbers and use them directly. So what we do is we take these numbers, this response here in terms of numbers, and subtract it from a slightly larger number, and then we end up with this. And the beauty of that is it's silent. There's no mixing going on, there's no analog going on, there's nothing going on. It's just all math, and math doesn't make any noise. I mean, except for maybe truncation. But, we're not talking about that sort of thing at all. It's like, it's completely silent going from here to here. We take no signal noise hit. So that's nice. But we end up with the same curve. But here on the D-Lev, where the curve would go negative and the field would reverse on an analog theremin, we can just say, well, we don't want those negative numbers, and we can just throw them out. So it comes for free, the pegging of the field at the null point. So that's nice. That's kind of an added thing that doing this mathematically, another nice thing that doing this mathematically gives you for free. The field won't reverse on you. So that's nice. So we want to go from here, and we want to get rid of the squirrely portions at both ends, and like, how do we do that? Well, the thing I stumbled across in a spreadsheet finally, I was about to give up actually, was very, very simple. We take this and we raise it to a fractional negative power. And the linearity knob on the D-Lev, the range of it is between -1/8 and -3/8. So the nominal point is -1/4. And when you do that, boom, you get this almost straight line here. And it doesn't have any of the squirreliness at either end. It's wonderful. And then if we alter the power somewhat, like with the knob, we get a slight either bump here or a slight dip right here, right near the antenna. But that's it. Otherwise it's linear. And it's just a very mild kind of control over to adjust the linearity of this line. So I mean that's it. I mean, it's kind of that's how the D-Lev does linearization. It's remarkable. It's remarkably easy to set. It just works extremely well, and I'm hoping this method is used, or something very similar to it, in other theremins. I mean, basically what you're doing when you raise something to a negative fractional power is the negative means that it's an inverse, so that you're actually kind of looking at the period rather than the frequency. And so, you know, if you're measuring period instead of frequency, you might be able to you know, incorporate this method somehow that way by taking that into account. And then also, when the power is fractional, that means we're actually sort of taking a root rather than raising it to, you know, we're not squaring it, we're maybe more like taking the square root, or we're taking the fourth root, I guess, because it's 1/4. So this is inverse fourth root, I guess. So, you know, and if you just wanted to do that, you'd end up with something that works really good for just about everything. So what do the other knobs do? So this was obviously P-cal and V-cal. Right? This is the linearity knob, the lin knob. The next is we want to bring this down to the x-axis, and we do that so that we can pivot it about the point that it crosses the x-axis. And the OFS minus knob is what brings it down to the x-axis. And we have that knob just so that you can control where this pivot point is. Otherwise it can be a constant. The next knob is sensitivity, SDNS knob. And we negate that, and we do a multiplication. So we just take this, multiply it by negative sense, and we end up with this. And so the slope has gone from this to this, which is the slope that we want. And then we can control the slope, so we can control the pitch response to various hand gestures. You know, we want that to be an octave. You know, we set the sense slope here to a certain value, and then we get that. Or if we want it more relaxed, like I play it, like this to be 4 half steps, we can set that there, that too, with the sense knob. So that's the sense knob. And then after that, we need to raise it back up to use it over the useful frequency range of the human ear. And so we do that with the OFS plus knob. So if we want a certain frequency right at the antenna, we can move this whole line up and down with the OFS plus knob and get that frequency right at the antenna. Or if we like certain mid frequencies to be in the midfield, we can just move it around. So there you have it. Cal, Lin, OFS minus, sense, OFS plus. And please use this. I would love to see this or something very similar show up in every theremin and give everybody really, really good linearity. All right, thanks.